10:30. We've got a couple of hours. I think we can get through the material. If we run short of time, then what I will do is complete the whatever we miss at the end. Just keep recording even if you have to go. And that way I can post the whole thing on Blackboard, whatever we've missed. But I'm counting on getting through the whole thing. All right. Start the slideshow. There we go. All right, all this stuff we've done up till now is to get you ready for the real meat of chemistry. That's better. Stoichiometry. It's a big word. Invented by a German toward the end of the 19th century. It doesn't have a direct translation that really makes a lot of sense, but I did find this one reference to stoichiometry as countable versus uncountable. In other words, if you can put numbers to it, it will fit in stoichiometry. If you can't put numbers to it, then it doesn't fit. Like the reaction turned blue. That doesn't work in stoichiometry. You got to have a number associated with it. And that's why the classical definition is the study of quantities of materials consumed and produced in chemical reactions. So you're keeping track of what goes into the reaction, what comes out. That's stoichiometry. But we've got a little problem, is that we can't see atoms, so you can't count atoms, right? So what we've got to do is come up with a different solution, and that solution is counting the atoms by weighing them. Right, so here's how it works. First of all, you have to assume that all your atoms are behaving as if they were identical. And that is, if you've got a reaction that involves carbon, then you keep track of all the carbon atoms. And if there's also hydrogen in there somewhere, you got to keep track of the hydrogens, so forth and so on. But each one of those behaves the same as far as its mass goes and the number of atoms that relate to that mass. So in order to do that, we need an average mass of each of the objects, or the average mass of carbon, the average mass of hydrogen, the average mass of whatever else you have in there, whatever element you have. You need an average mass. And that's what this value means. It's not going to show up there. Right here. We know what this one is. That's the number of protons, the atomic number. This is the atomic mass. Now that's different than the mass number. Remember, the mass number is the total of protons and neutrons, and that references the nucleus. So that can vary depending on how many neutrons are there for each element, which is where isotopes come from. But this number is, we like to say, operationally defined. In other words, an average sample of the element is taken from nature, what you're likely to encounter in nature, the average sample, and then the mass of a certain number of those atoms is determined, and that's what you get. Okay. So we need to know an average mass of the object. All right, here's an example. Suppose you have a pile of marbles, and we put them on the balance, and they turn out to weigh 394.80 grams. And you count the number of marbles. Okay, this is a starting point, 394.80 grams. Let's put that here. And yeah, it's up there, but I like to write it anyway. That's the total mass of your marbles. But instead of counting all the marbles, let's just take 10 of them. So we count those 10 marbles, and they weigh 37.60 grams. Okay? Notice what we have here is 10 marbles equals 37.60 grams. We have an equivalence. So automatically we have what? Conversion factor. Whenever you have an equivalence, you've got a conversion factor. It just depends on whether you put this one on the bottom or that one on the bottom. Whichever one you need, right? You've got grams here. If you want to find out how many marbles there are, you need, right. No, grams on the bottom.
Grams on the bottom, yeah.
And marbles on the top. This way, the grams cancel and leave you with marbles. So we have 37.60 grams and 10 marbles. So there's our conversion factor. And what we're doing is we're counting the number of marbles by weighing them. We weighed that many of them to find this equivalence. And now, since we know that's the relationship of this many marbles to that mass, we can use that to find out how many marbles we have as a conversion factor. So it turns out we have 105 marbles. Any questions? Okay. We're going to do the same thing with atoms. But we need a standard. So for the longest time, the standard was oxygen. And it was assumed that each oxygen atom was 16 atomic mass units. But it's difficult to handle gases and get a purified gas to weigh and standardize. So eventually we switched over to carbon. So for the carbon 12 there, wait a minute, that's not right. 6. We take this isotope of carbon, right, which has 6 neutrons and 6 protons. That's your standard. And that's taken as exactly 12 atomic mass units. That's our starting point. Now, there are other carbons, right? So we have carbon 13, and we have carbon 14 isotopes, okay? And they will roughly be 13 atomic mass units and 14, but not exactly, because this is the only one that's set at 12.00000000, however many zeros you need. And we compare the others to that one. Now, for argument's sake, and for the sake of the calculation, we're going to assume for the moment that that one is 13 and this one's 14. And the calculation comes out pretty close anyway. So it's kind of like doing your GPA. It's a weighted average, right? A lecture course is either 3 or 4 credit hours. So the grade you get in it, say you get an A in a course, you got 4 quality points. And for this course, it'd be 3 times that is 12. But to get to average, you need to find out how many credit hours you're taking, and you divide your quality points by your credit hours. That gives you your GPA. It's a similar concept to getting the average atomic mass for carbon in nature. You have to know how much of each one of these you have. And you can do that with special equipment. Spectrometer will actually count atoms, right? We can't do that in most labs because the equipment is too expensive, and it takes a specialist to know how to operate it properly. So we have people doing that. They spend their whole lives. A lot of them work for the NIST, National Institute for Standards and Technology. That's all they do. They just check these things over and over again. And sometimes, each time a new chart is generated and produced, it'll have a date somewhere on it. This one was created in 2014, but it's based upon standards that were established in 2005. So the next one, maybe the next one come out in, I don't know, in 2020. It'll come out with a new set of standards, and these will shift slightly. Now, for scientists that are doing really, really detailed, accurate, precision work, those numbers are very important. But for us in a student lab, they're nearly always going to round off to 2 decimal places the same, no matter how accurate they are into the future. So they use this equipment, and they determined that in a natural occurring sample, carbon-12 is most of it, 98.89%. Carbon-13 is a little over 1%, and carbon-14 is less than 100%. So you can basically ignore that one. So what you would do is you would take this one and use the decimal equivalent of that number, 0.9889, times that one, and this one would be 0.0111. And you would get a value here, then you would just add those together.
So how did they find the percent of like 13?
With a spectrometer.
Oh, okay.
Yeah. It actually counts the number of atoms. I think I've got a picture, a diagram of one in here. Yeah, it's coming up. So, if we multiply that percentage times this one, actually decimal value, times that one, and add them together, we get a value that's about 12.01 atomic mass units. Sometimes they abbreviate it with just a U. It means the same thing as AMUs. So that's why this value here is 12.01 and not 12, because you're incorporating all of the isotopes that are naturally occurring and their abundances. So now that we know the average mass of carbon in nature, when you take a sample and you weigh it, say you have a sample of pure carbon obtained from nature, and the weighted average has already been determined, all you have to do is weigh the sample, and you can convert that to numbers of carbon atoms. Because this value, 12.01, atomic mass units, is per atom. Right? So if you know the number of atomic mass units you have, then you can find out how many atoms you've got. We're going to come up with a different unit of measure. Atomic mass units is okay for discussion purposes, but you need something a little more useful than that. So it's coming. There's your mass spectrometer.
Oh.
So all it does is it ionizes the atoms and accelerates them and collimates them. That is, it makes them go faster because the atoms are positively charged and the plates are negatively charged. So you get those ions accelerating toward the plates. If they smack the plate, they won't go through, right? If your source is here, right, they're going like that, then you're going to get kind of a broad there. So you put another one here. So only the ones that are lined up perfectly with that one and that one come out straight. That's called collimating, making straight. Now once you've got your ions flying fast and straight, you run them through a magnetic field. And of course, charged particles going through a magnetic field makes them bend. So they bend, but the ones that are lighter, they're all going the same speed. The ones that are lighter bend the most because they have less momentum, so they bend like that. The ones that are heavier bend like this. And on the other side, the heavy ones come out over here, the light ones come over there, and your detector counts them. Modern electronics can count that fast. So that gives you a percentage of each of the isotopes in your sample. Okay. So let's say we have 62.6% of an isotope with this mass and 37.4% of an isotope with that mass. So it's 186.956, 86.956 times 6260%. Okay, that's the contribution of this isotope, the contribution of this isotope, so 184,953, is 37.4%. Okay, so let's see how much one contributes. If we'll have to do this one by hand. 186.956. 0.626 times is that's its contribution. And then 184,953.374. This one is 6917. Oops. Okay. Now add them together, and I get 186.21 as the average mass of that element. Now, can we use that to determine what the element is? Average atomic mass, of course, got that value already. But can you use that to find your element? Yeah. We've already said that atomic numbers determine the element. But if you have an average mass determined already, and you can find it on the periodic chart, chances are good that you're going to be able to identify the element just as well. 186.21. 186.2071 is this element. I didn't have you memorize that one, I don't think. It's called rhenium. Okay. Now, there are rare occasions where you might determine the average atomic mass of an element, and it'll be halfway in between one or the other. All right. So it's not as definitive as the atomic number, but you can usually get pretty close. There's some that are very close to one another. Let me see if I can find them. Like potassium is 39.1, argon is 39.9. That's far enough apart. I was looking for a better comparison. There are 2 or 3 places in the chart where average masses are really close. Now, if you're doing this for a living, that would be a concern. But if you're trying to pass a test, I'm not going to give you one that's that iffy. If I give you a problem like that, you're going to be able to find it. Okay. Now, here's that unit of measure I was talking about, the mole. It's not the furry little creature that digs up your lawn. The mole is a unit of measure. The mole is a number of things. It can be a number of any things. Usually, for our purposes, be the number of atoms would be a mole. 6.022 times 10 to the 23rd. It's a huge number. Or ions, or molecules, or chickens for that matter. You can have a mole of chickens. You have trouble finding space for all of them, but it's possible. It's also called Avogadro's number, named after the Italian chemist whose concepts led to its development. I don't think he ever determined that number, but they give him credit because of the work he did was pivotal to establishing the relationships that the mole allow us to consider. So the mole, 1 mole then, is this value of anything. Now, the nice thing about it is, we determine that the average mass of carbon in nature is 12.01 atomic mass units. If you have a mole of carbon atoms naturally occurring, so there'll be a mix of isotopes in that, but if you have a mole of them, this many, that carbon will weigh 12.01 grams. Okay? I left my E off. I'm abbreviating. No, it's real. That's the way you write the whole word, and this is the way you abbreviate it. Tell me that makes sense.
So for like carbon atom, we would have to put grams, or we have to do 1 mole.
If you have this many carbon atoms, yep,
Okay.
together, they will weigh 12.01 grams. Okay? So, every one of these values for each of the elements is 12.01 grams per mole. So every element has a conversion factor built in, that number, that many grams per mole of atoms. Okay? We're starting to get more and more information from the periodic table. Okay, so if we have, let's say we have 4.48 moles of iron atoms that we've purified from nature. Of iron. And we want to know how many atoms does that represent. You want to convert that to atoms of iron. So you need atoms where? On top, right? That's what you want to end up with. And you want to cancel out the moles. Right? That's your conversion factor. That's how you build a conversion factor. This is where you headed That's where you're coming from. Coming from goes on the bottom, headed goes on the top. That's so you can cancel the moles. Because this is numerator, that's denominator. This is numerator, that's numerator.
So you write down 1 mole on the bottom.
Mm-hmm. And what it's equal to on the top.
Would be,
A big number.
yeah.
So you multiply. Now that we've got the moles canceled, left us with atoms. 4.48 times that value will give us 2.70 times 10 to the 24 atoms of iron. So we have counted the number of atoms. Well, actually,
Where'd you get the 6 from on top of that?
that's the value of a
That's the
mole.
value for the mole, huh?
Yeah, previous slide. Right there.
Oh, okay.
Okay, so if you got your calculator set up correctly to spit out answers in scientific notation, it should give you that value. Okay, let's try another one. We're given. This is also called the molar mass. The molar mass is what I said earlier, that many grams per mole. That's the molar mass. Sometimes I revert. Years ago, instead of calling it molar mass, we call it atomic weight. And when we get to calculating the weight of a mole of molecules, I may say molecular weight instead of molar mass. But I'll try to give you both of them at the same time so I won't be confusing anybody. Molar mass of nitrogen is 14.01, right here, rounded off to 2 decimal places. So that's adequate. If you round it off to 2 decimals, you'll be fine. Molar mass of water then is what? Well, how do you do the molar mass of a molecule? H2O. Well, it's going to be the mass of water when you have a mole of water molecules, right? So if you have a mole of water molecules, how many moles of each of those atoms do you have? Right? This one you have 2 moles of hydrogen, right?
Yeah.
Okay, and you still have 1 mole of oxygen, right? So 2 moles of hydrogen is what molar mass? Well, we go over here, round it off to 2 decimal places. Hydrogen is 1.01 grams per mole. And oxygen is 16, I think, rounded off to 2 decimal places. So you have 2 moles of this one. Two moles of that one, which is 2.02 grams. And 1 mole of this one, which is 16 grams. So we have 18.02 grams per mole of water. So all you have to do is just count up how many of each atom is in that molecule, and then use the conversion factor or the molar mass for each one times how many you have. Just add them up then. Any questions so far? Let's go to,
So for
yeah.
H2O, we just add like 2.02
Mm-hmm.
16
Mm-hmm.
point.
Yep. So let's pick one that looks really hairy, like barium nitrate. Okay. How many bariums do we have? 1 mole. Okay. Barium is a heavy atom, 137.33. Okay. Anybody ever had a barium swallow or a barium enema?
I've heard of barium enema, but
They use it as a contrast agent.
yeah, I'm not actually had one personally.
so they can take an X-ray and it brings out the definition of your colon. But barium is a huge atom, and it's very good at attenuating X-rays. They don't use barium nitrate, they use barium sulfate, because barium sulfate is insoluble. That is, they can give it to you by mouth or the other end, and you won't absorb any of it because it's not soluble. So it won't be toxic. Okay, back to the topic. How many nitrogens do we have? Right, 2.
Six.
You have 2 of these. Nitrate is a polyatomic ion. That's why it has to be written that way. But you need 2 of them to balance the barium, because barium is a 2+ charge and nitrate's a -1 charge. Right? So 2 minuses balance 2 pluses. But now that we've got the balance correct, 1 barium and 2 nitrates, now we need, how many nitrogens do we have? Well, we've got 2 nitrogens, because this 2 propagates through the entire parentheses. So we have 2 moles of nitrogen, which is 14.01, I believe, grams per mole. How many oxygens do we have? 6. 6 moles of oxygen. And we just did that one, 16 grams per mole. Okay? So you just multiply this one out. Well, 1 times that is, and then 2 times this one, and then 6 times that one. See if I can do that with my head. Is that right? 96? Yeah, I think that's right. Then add those together. And it should be 261.35. Yeah, 0.35, that's right. Yeah, carry the, yeah, 261.35. And this is grams per mole of barium nitrate. Okay, that's how you do the molar mass of a compound. Okay, any questions so far? Let's see how we're doing on time. Okay. Which of the following is closest to the average mass of 1 atom of copper? This is really kind of easy. If you have good test-taking techniques, you can process of elimination figure out which one of these is right without knowing anything about copper. Based on what we've determined so far, you need a whole mole, 10 to the 23rd atoms, to be measurable, or something in that range, right? So 1 atom of copper is not going to weigh grams, right? Whole grams. Can't be. So by process of elimination, that's got to be it. You know. But we can actually calculate what 1 atom weighs. So if you're starting with 1 atom of copper, then you want to find out if we're going to convert that to grams, we need something in terms of moles and grams, right? But we don't have moles yet, so we got to figure out moles. Okay, now that we have moles, we can convert to grams because we know what the average, the molar mass of copper is. And we can convert mole into grams. So we look over here at copper, 6355, rounded to 2 decimal places. There we go. Now, the rest is just number crunching. 1 times 63.55 divided by 6.02 times 10 to the 23rd. And that's going to come out to this number right here. Unit conversions. Yes.
Okay, is 6.022 times, is that?
Oh, sorry. Yep, 10 to the 23rd. Don't let me get away with anything. Stay on your toes so I can stay on my toes. Yep, that should have been a power of 10. All right. Here's a logical question. We should be able to do this one without even calculating. How many copper atoms are in 63.55 gram sample? 63.55 gram sample is 1 mole, isn't it?
Yeah.
So you got 6.022 times 10 to the 23rd atoms in that many grams. Okay. Okay, let's complicate it some. So you've got magnesium and zinc and silver.
Got 100 grams, same for each.
100 grams of each, right? Okay, the question is, which of the following contains the greatest number of atoms? So this forces you to think about, if you've got a mass of something here and a mass of something here, which one is going to have the most number of things in it? The one that has the smallest mass for each individual one, because they both have to add up to 100 grams. So the lightest one, you're going to need more of them, right? So magnesium is 24.31 grams per mole. Zinc is 6538. And silver is 107.87. All right. Which one's going to have the most numbers?
Magnesium.
Right, because it's the lightest one. It's going to take more of these to make that mass than one of these. So this one's the lightest one. Let's put them in the order of, what does it say? Oh, it just says which one's the greatest number. Okay, so that's the greatest number because this one is going to be the fewest, this is going to be next, and this is going to be the greatest number. Okay? Now let's make it worse. We got a different mass for each one this time. We're going to need that information, so I'm going to leave it up there.
So we're going to find out what percentage.
Silver is 107.9 grams. Zinc is 70. And magnesium is 21. We don't actually have to calculate this one. It says order from greatest to least numbers. Right? So which one is going to be, is there anyone going to be equal to a mole? This one. So that's equal 1 mole. What about this one? Greater than or less than a mole? greater than a mole, right? And this one is less than a mole. Okay, so from greatest to least, this is greatest to mole, so zinc, and then equal to a mole, and then what's left over. So that's the order. These masses give you this order. You've got more of these, then you do these, which you have more of those. Okay? So you don't actually have to sit down and punch it in your calculator. Just use a little logic. Okay. So let's make things even worse. You've got 100-gram samples of each one of these. Okay, here's where I invoke Henry Ford. Set up an assembly line so you can do the same thing over and over and over again. Once you've got the process down, then you just repeat the process for each one. So water, nitrous oxide, or dinitrogen monoxide, C3H6O2, that's probably propionic acid, and then carbon dioxide. Okay, you've got a 100-gram sample of each. So here we go, setting up our assembly line. That's your sample. And you want to convert it to numbers. Now, up to this point, we've said numbers are actually numbers of atoms. But remember that the mole is actually another unit of numbers, right? So if you find out the number of moles, you don't have to go all the way to actual numbers of atoms. When you're going to compare numbers, all you need is how many moles.
You compare the moles.
Compare the moles, right? Okay, so this one we want to convert to moles. We determined that earlier to be 18.02 is 1 mole. Nitrous oxide. How many grams of that one? Well, you need 2 nitrogens times 2, and then 1 oxygen. So 2 times this one plus 1 times that one is it's 2802 and 16. So that's 4402 grams per mole. And remember, conversion factors, it doesn't matter if you flip them this way, flip them that way, they're still equal to 1, right? Since that's equal to that, dividing one by the other, it doesn't matter what order they are, it's still 1. Right? So you can flip them however you need them. We need grams on the bottom, so that's why it's this way. How about this one? We need 3 times carbon. We need 6 times nitrogen, hydrogen, excuse me. And then 2 times oxygen. So that's 3603 on top. And then 6.06 plus, and then 32. 7309. So this one is 73.09 grams per mole. Grams on the bottom, moles on the top. And CO2. So that's 12.01 for carbon. And 32 for oxygen, right? 2 times 16. 4401. There we go. Our assembly line. We're doing the same procedure. The only thing we changed was this value right here. And that's going to give us the number of moles of each one. So 100 divided by 18.02 is 5.55. Actually, 549, right? 4 significant digits. Because it's 1, 2, 3, 4. These don't count because they're exact numbers, right?
Yeah.
But these are the ones that determine that value. So that's how many moles of this one you got. Then 100, 44.02, and I get 2.272.
So we still have to go through and do like every single one, because asking for just the oxygen atoms.
Yeah.
Okay.
Yeah.
That's all.
This is moles. This is moles of water. This is moles of nitrous oxide. And this is 73.09, 1.368 moles of this compound. And then the last one, 2.272 of CO2. Okay, that's the number of molecules. Now, the number of oxygen atoms. If you have this many moles of the molecule, how many moles of oxygen atoms do you have? Well, it's different for each one. Well, actually, the same for these two and the same for those two. This one only has 1 oxygen for each one. So it has the same number of moles of oxygen as the compound, because they're 1 to 1. 1 oxygen, 1 molecule. This one's 1 oxygen per molecule. Okay. This one has 2 for every one of these moles. So let's see. That's 13, 1, 6, 7, 2. So that has 2 times as many oxygens as the molecules.
So would we kind of like times that number by 2?
Yep. That's what I was trying to do in my head there. And this one is also 2 for each one. Now you can set that up as a conversion factor if you want. You just have a conversion factor here. Moles of water on the bottom is 1. Moles of oxygen on the top is 1. And this one's 1 and 1. This one's 1 and 2. This one's 1 and 2. So this one would be 14, 4. Now we can compare. Greatest to least. Okay, so this one's the greatest. This one's next. This one's next. This one's next. Okay? See if I did those right. Water's the greatest. Yep. Then CO2, then propionic acid, then nitrous oxide. So that's the assembly line. You set it up, you know how to do this one, you know how to do the rest of them. You just have to be sure that the right numbers are there. But the process is the same. This is the author's idea of problem solving. But I would just say, for step number 1, what's the question? Their idea of where you're going is, what's the question? If you don't know what the question is, you're not going to get the answer. Then how do you get there? You devise a strategy. You say, if the question is this, what information is in that problem that will give me the answer? Or do I need to go out and get other information? For instance, do I need to go to a periodic table and get that information? Because you'll always have one of those. You'll always have useful information too. That's another reason for studying the review document, because the last few pages are useful information, and those pages will appear on the exam. If they're in the review document, they'll be on the exam. And then once you've used that information to get an answer, ask yourself, is that answer reasonable? Does it make sense? Okay. So before we can use balanced chemical equations to determine what goes in, what comes out, we need to settle on some agreed upon ways to determine how much of each element you have in your sample. Up to this point, we've found that if we know the formula, then we know how many atoms of each one, or how many moles of each would be in a mole of that compound. Okay, that's fairly straightforward. But you rarely have that to begin with. If you're a bench chemist and you're given a sample, and say they're kind, they say the sample's pure, right? It's a pure compound, so you can take it from there and find out how much of each element is in there. So you go through certain steps and you determine, well, this sample weighs so many grams, maybe 100 grams. And say 30 grams of it is carbon and 20 grams of it is hydrogen, and maybe 30 and 20, 50, so I think it's 50 grams is oxygen. So once you determine those values, then you can do a percentage based on the total that you started with. Right? That's what we're doing here. So the mass of each element, mass percent, you just take the mass of the element and divide by the mass of the compound times 100. Okay, it's fairly straightforward, but that's typically what you get from an analysis of a compound. You get percentage values. Now you can do that on the bench, do your wet chemistry and find out what each one is, but you can also work backwards. Once you've got the compound formula, you can determine the percent of each one in there. You just assume that you have a mole. Right? So if we have a mole of this compound, say 1 mole, how much will it weigh? Well, it's going to have 2 irons right here, right? 2 irons, grams per mole. It's going to have 3 oxygens right there, right? So that's 1 mole is that total mass. So that's your total mass if you have a mole. If you have a mole and you're interested in the iron, then the mass of the element is 2 moles of iron for every mole of the compound, right? So you have 2 moles of iron up here weigh that much, and 1 mole of the compound weighs this much, right? Notice that when you're doing this way and you're determining the percent composition of your given compound, you will always have this one in both the numerator and the denominator because it's part of the total. Don't forget to do that. It'll mess up your answer.
Okay, so for mass of the compound, which is the iron, which is both right in there,
Right here.
which is 55.85
grams, right? It's kind of small there.
Okay, well, I found it. I was figuring out how they got it, but
Yeah, it's right there.
took it.
Right here. So you got this in the numerator, that's the element. You got this in the denominator, that's the total compound. Divide them times 100, that should be at times. And you have 69.94% iron by weight, or the mass percent. Okay. We're kind of running out of time. So how would we, let's say, how would we do this problem? You got those same compounds again. Rank them in the highest to lowest percent oxygen by mass. So you would just take, what's the total mass of water? We did that one before, 18.02, right? Divided into the mass of oxygen, which is 16. So 16 divided by 18.02 times 100 would be that percent. And you just go down the line. The denominator would be the total molar mass of each one, respectively, and then oxygen on top. This is only one oxygen, so that's 16 again on top. But that's two oxygens, so that'd be 32 on top. And this one would be 32 on top. And you could determine the molar mass of each one and find that the order of percent oxygen, actually water has the highest percent oxygen of all of them. Oops. Okay. Definitions. What do we mean by empirical formula? The empirical formula is the simplest whole number ratio of elements in a compound. So if you had this one, or you had this one, two good examples. The empirical formula for both of those is exactly the same. The simplest whole number ratio, you can divide 2 into this one, and you get that. Right? That's not the simplest whole number ratio, right? Because you can divide it by any number and reduce it. So we divide by 2, divide this one by 6, and you get the same empirical formula. That gives you the ratio of moles of each element in the compound. Now that by itself is not much use, but it is a stepping stone to finding out what the actual molecular formula is. The molecular formula for this one is different than that one. But notice, if we multiply this one through, we get that. If we multiply this one through, we get that. So this number is the one we're looking for. Now, this is not the same as when you write a compound, like we had our barium nitrate before. That too has to stay out there. But for our purposes here, we want that number to propagate through. So that's C6H6, and this is C2H2. So I'm using a different convention. So what we need to do is first use our data, percent composition that's given, to find out what's the empirical formula. Then we need another piece of information that tells us what's the molar mass of that compound. And then we can use the molar mass to tell us what this value is, and that will give us the molecular formula. So we're going to run through the steps, try to get through them before I run out of time. Okay. Oops. This is just an example of how you determine composition a bench chemist would use. This is known as a what do they call it? An absorption train. Let's put it that way. So you blow oxygen through your sample. This is particularly good for organic samples. And it converts everything to, when you burn your sample, carbon dioxide, water. So we pick up the absorb the water here first, and we know how much that weighs beforehand. So we just pull it loose after we finish the experiment and weigh it. We find out what the difference is. That's how much water is absorbed. And then this one goes through and picks up the carbon dioxide, and we do the same thing. We just weigh it before and after. So we know how much hydrogen was produced and how much carbon was produced. We can't do the oxygen because we're blowing we're blowing oxygen through there, just mass quantities, as the coneheads would say. Nobody knows coneheads? No? Okay, never mind. I'm going too far back. But if you know that carbon, hydrogen, and oxygen are the only elements in your compound, then if you determine two of them, you got the third one by difference. Okay, so let's use this to determine empirical formula, molecular formula. The data that's given is percent composition right here and here, here. And then for the second step, we have the molar mass. My batteries are going out. Okay, Henry Ford time. Carbon, hydrogen, oxygen. Okay, what's the percent composition? Well, carbon is 49.3%. Hydrogen is 6.9%. And oxygen is 43.8%. And those are the only elements in your compound. Okay. So, in order to determine the empirical formula, we have to know how many moles of each one there are, right? Well, percent is a dimensionless number. It's parts per hundred, right? Well, we're told that it's mass. Right? That's the problem with percent. You got to say what percent means. Because it could be mass volume, it could be volume, it could be mass. In this case, it's mass. So it's that many grams per 100 grams of sample, right? So there's the clue. If it's this percent, let's assume that we have 100 grams of sample. You could actually assume any number, but 100 seems to be logical. Because if you have 100 grams of sample, then you know that you've got 49.3 grams of carbon, right? You got 6.9 grams of hydrogen and 43.8. Oops. Try that again. Of oxygen. Now we can convert to moles. We're really only interested in the ratio of moles of each one, right? So the choice of 100 grams is just convenient. The ratio is important. So now we've got an assembly line going here, and we're going to convert to moles of each one. What do we need? Grams on the bottom, right? Because we have to cancel the grams. Moles on the top, because that's where we're headed. Okay? So carbon is what? 1 mole is 12.01 grams. Hydrogen is 1.01 grams. And oxygen is 16. Okay? Now we can find out what the ratio in moles, numbers of atoms, because the formula, the molecular formula of a compound, whether it's empirical or it's the true molecular formula, is the ratio of numbers of atoms in the compound. Not mass, numbers. Okay. So if we do 49.3, we get 4.105. And 3 numbers, 1 moles of carbon. And 6.9 divided by 1.01 is 6.83 of hydrogen. And oxygen is 43.8. Divided by 16 is 2.34, 2.74. Oxygen. Okay, so there we have established a ratio. Well, what's the definition of empirical formula? It's the simplest whole number ratio, right? Are any of those whole numbers? No. But the ratio is established, we can make them whole, right? The simplest way to make whole numbers out of these is divide everything through by the smallest one.
So we're dividing by like oxygen because it's smaller than
It's the smallest one. So this one is 1. 6.83, 2.74. This one is about 2.5. Now this time it's okay to start estimating, drawing things down, because experimental error is never going to give you exact whole numbers. You have to use logic. So 4. Is that right? Yeah, 4.11. 2.74 is 1.5. Now we're getting closer. This one's whole number already. So can we multiply all those by a number, a same number? Here we divided by the same number. Can we multiply these by a number and get whole numbers out of that? Right. The key is half. Multiply half by 2 and you get 1. So if we multiply all of them by 2, we get 3, 5, 2. So we have carbon is 3, hydrogen is 5, and oxygen is 2. That's the empirical formula. And then you want to check yourself. Say, is that the simplest whole number? Yeah, you can't divide that through by anything and simplify it further. The clue is you've got an odd number, a prime number, and an even number. You're not going to find a divisor to reduce those any further. So that's the empirical formula. Now, how do we go from there to the molecular formula? Well, we want carbon, hydrogen, oxygen. So we got, well, I'll do it down here. We want a multiplier here, propagated through, that will give us that will give us this value. Okay? So we know how to get the formula weight from our information, but we don't have the formula weight yet. Well, we do have the formula weight, 146. But from this, we could get an empirical weight, right? What's the weight of just that? And compare the two. So 3 carbons and 5 hydrogens and 2 oxygens would be what? Well,
5.05 is the minimum.
okay.
36.03.
03?
Yeah.
And 32. So that's 73.08. So the empirical formula for this one is 73.08. And the molecular weight is 146. Just like that. So if we ratio these two, right? If x is equal to 1, this should be 7308, shouldn't it? Right? Because it's the same formula for both of them. If this one's 2, then this one should be double that one, right? Which is what we got, right? X equals 2, because this one is twice that one. Or just take this one, divide by that one, gives you a number. And you want the simplest whole number. So X equals 2, that means the molecular formula is C6H10O4. See if I did it right. Yep. That's how you go from percent composition to molecular formula. Okay. All right, so now we're going to write balanced equations. An equation, chemical equation, is an expression on the macro scale, what's going on the micro scale. The equation is a representation of what compounds are reacting, or elements for that matter, to produce products. So reactants are on the left-hand side, products are on the right-hand side, with an arrow in between. That's the convention. You write the formula, the molecular formula here, or the elements, and then you say, how many do you have of each one? A balanced chemical equation is only numbers. Numbers of things, not mass, numbers of. So 1 mole of this plus 3 moles of that yields 2 moles of this and 3 moles of that. That's the way you read it. Or it could be 1 molecule of this plus 3 diatomics, right, yields 2 carbon dioxide molecules plus 3 water molecules. So you can read it either as moles or as individual molecules or atoms. Okay, the way this one is given, we're balanced. And the way to tell whether we're balanced or not is, say, C2H5OH plus 3 oxygens yields 2CO2 plus 3 water. So I set up a budget, right? What are the elements? Well, let's see, we have carbon, we have hydrogen, we have oxygen, and that's it, right? So how many do you have on this side? We have 2 carbons, right? We have 5, 6 hydrogens, and we have 1 plus 6 is 7. 7 oxygens, right? That's what you're starting with. Remember the conservation of mass in a reaction? That's a law. So you need to have the same numbers of each one on both sides if it's balanced. So carbons, 2 carbons here, hydrogens, 6 hydrogens, and oxygens, 4. 4 plus 3 is 7. So that is, in fact, balanced as written. Okay. So your textbook will probably say, if you're given an equation that's not balanced, let's say all you're told is these 2 reactants give these 2 products or 3 products, whatever it is. Right? Then you write them up here. You have to write the compounds, if there are compounds and elements, correctly. This plus that yields this plus that plus whatever. You have to write the compounds correctly. That's why I hammered learning how to write compounds from the names. So if you give them the names, you've got to be able to write the compounds. Otherwise, you're stuck, just spinning your wheels. So once you've got those compounds written correctly, then you balance the equation. I used that budget method. Most chemistry textbooks say balance by inspection, which is a cop-out. They're not going to tell you how to do it, right? But any chemistry teacher worth his or her salt will give you a method, right? So that's what I'm going to do. So these are the steps, but it's probably better if I just show you. Right? There are helpful hints. And in your, let's see, did I put them in here? Yes, on page 5. That's where we are in our PowerPoints. The bottom right corner. I go through one there and show you step by step, but without the animations, it's a little hard to follow. And there are helpful hints that I also include there in the previous 2 slides plus that last slide. Things to do that will simplify things. The first rule that will help is if there's an element, a single element like that oxygen, if it is only one place in the reactants or products, then save it for last. Because if you change the coefficient of that one, and by the way, those preceding numbers are called coefficients. If you change the coefficient on that one, it doesn't change anything else, right? So save it to last. Because the last thing you want to do is change the coefficient on a compound and, oh, I got that element right, but it screwed up this other element. Now I got to go back and figure out what to do with the rest of it. Right? So save single elements till last, like this one, right? It only appears here on that side. Save it till last. We're going to save water till next to last. Let's see. The convention is once you reach the end and you have a balanced equation, you should have no fractions as your coefficients. They should all be whole numbers, right? Because a fraction of a molecule means what? Nothing. Right? For calculation purposes, you can use fractions. And I'll hopefully show you an example. Well, here's an example. In order to reach the end, I found it convenient to use a fraction here. But once you've got the fraction in there and your budget is balanced on both sides, then you get rid of the fraction. So if it's a half, something half, you just multiply the whole thing through by 2 and you get rid of that fraction. That's what I've done in this example. I have to show you one. We already said that. Oh, polyatomic ions. If you've got polyatomic ions in your reactants and the same ones in your products without any change, in other words, the reaction does not break apart a polyatomic. If the polyatomic survives the reaction, both sides, then it's simpler to, when you set up your budget, say we have nitrate, NO3 on both sides. Just write it as one of your terms, nitrate on both sides. That saves a lot of trouble. For instance, here we've got ammonium on that side, nowhere else in here, and only over here. So that's valid. Use ammonium. We've got phosphate here, phosphate there. So use it as one of your terms. Rather than breaking it up into nitrogens and hydrogens and phosphorus and oxygens. It can be done that way. It just takes a whole lot longer. Okay, so the animations are going to go through and show you that. let's do this on the board and run out of time while we're at it. So here's our ammonium phosphate. But first of all, is that written correctly? What's the charge on ammonium? It's a polyatomic.
3.
+1. Ammonium is +1. It's the only positive polyatomic in your whole chart. Phosphate is 3-, right? So you need 3 pluses to balance the 1, 3-. That's written correctly. Calcium chloride. Chlorine is a halogen with a -1 charge. Calcium is a alkaline earth, which is 2+. So you need 2 minuses to balance that one. Then you have calcium phosphate. Make some space there for the coefficients. So 2 times 3- is 6-, and 3 times 2+ is 6+. That's balanced. A balanced equation. And then ammonium chloride, -1 +1. That's good. Now, for simplicity's sake, I'm going to leave out the phases here. Aqueous. Well, that one didn't even have one. That should be aqueous also. Solid, aqueous. Now, let's do our budget. So we've got ammonium on both sides. We can make it one of our terms. I'm not going to write the charge in there because we're just budgeting. We've already done the charges and we know they're correct. So ammonium on both sides, phosphate on both sides, calcium on both sides, and chlorine on both sides. Then you do your initial inventory. How many ammoniums? 3. How many phosphates? 1. 1 calcium, 2 chlorines. And you go over here, you have 1 ammonium, 2 phosphates, 3 calciums, and 1 chlorine. So that's obviously not balanced yet. All right. The first question you're probably going to ask yourself is, where do I start? Sometimes, no. Practice, 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 and you'll start getting a feel for where you should start. But even if you don't know where to start, I just start at the top. You're eventually going to get to the same place. It just might take a little longer. So let's see what happens if we do start at the top. Ammonium. Well, if we put a 3 over here, and remember, you can only balance once your compounds are written, your elements are written, you cannot change the subscripts, right? Anyone who does that is evil. You can only change the coefficients. So if we put a 3 in front of that one, that gives us 3 ammoniums over here and 3 chlorines. Okay? So ammoniums are done, we think. Sometimes you have to go back and do corrections. We could go in and tackle chlorine right away, but I think we should go to phosphate next. We got 2 phosphates there. Well, that really doesn't matter. Well, okay, let's go to chlorine. We changed chlorine to 3, so we can't change that one to 3, not unless we use a fraction. And I usually only use a fraction at the very end if I need it. So let's say we'll leave that one alone. We'll go to calcium, right? Let's say we need 3 calciums because we've got 3 over here and only 1 over here. How about that? That means we have 6 chlorines. All right, so chlorines are out of balance again. Let's go back up to phosphate and see what we can do with this one. So we need 2 phosphates here. 2 there. That means 6 ammoniums, right? 2 times 3 is 6. 2 times 1 is 2, right? So now we got phosphorus and calcium balanced, but our ammonium and chlorine are not. So if we go over there and try to balance ammonium, we need 6 over here, don't we? Okay, so that gets that one, and that gives us 6 chlorines. Now we're balanced. But one thing you'll notice is if you don't get these written correctly, you're going to spend the rest of your life trying to balance, and it'll never happen. Okay, that's why it's so important to get these compounds written correctly. Then they will balance.
All right, so because subscripts, we can only change subscripts.
Right.
Okay. So like on that side where we have chlorine, that is 2. And we put that 3 in front of that. That is going to make it multiple
Yes.
times.
That 3 propagates through the entire compound. So that means you have 3 calciums and 6 chlorines.
And then so on this side where we put the 6, that's going to make that all the way over here on the calcium a 6 too, right?
This makes the 6 ammoniums and 6 chlorines.
Okay, so that 6 will also make those chlorines.
Uh-huh.
6 too. Okay.
Right. Okay, so the animation is just fun. So that's our initial inventory. And then, actually, I went to calcium first. But that just proves the point. No matter where you start, you're gonna have a balanced equation eventually. Okay. This just emphasizes the point that all 3 of these are technically correct. But the best one is the one that gives you the smallest whole number coefficients. And that would be this thing. 2521. Yeah, definitely. All right, we're going to have to move along. So when we do stoichiometric calculations, what does that mean? When we do stoichiometry, we do introduce the concept of mass into our balanced equation. But in order to make it work, the equation can only tell you how much product you get. Say if you start off with a mass, how much product you can expect. You've got to go through numbers. So if you start off with 100 grams of this, you've got to convert to how many moles that is. Then you can do the transition to the other side. That tells you how many moles of the product. Then you go back and work backwards to mass. In other words, there's like a great wall here. Here, here, here. You can't cross that wall with mass. You can only cross it with moles. We're not even going to make it into chapter 4. So I'll create a video of chapter 4 lecture. There's not one in Blackboard now, but I will create it. Probably by tomorrow evening, I'll have it done and upload it to Blackboard, so you can get chapter 4. I'll just come in here and pretend that you're all sitting there and talk to you. Okay, so here's an example. And this equation has already been balanced for you because we don't want to focus on balancing right now. But if you get an equation, if you're given a reaction and masses of reactants, first thing you have to do is write the compounds and elements correctly in their positions, reactants, products, then balance the equation, then position the masses that are given to you next to the reactants and products, and then convert them to moles so you can make the transition to answer the question. But for our purposes here, this one's already balanced. Okay? So this is a solid, this is a gas, and this is a solid. And that's a very violent reaction. Every time you strike a match, you get that reaction. Okay, 6.25 grams of phosphorus. 6.25 grams of phosphorus is burned. What mass of oxygen does it combine with? Okay, we're assuming that all of this is consumed and you got plenty of that, right? You're not doing it in a bell jar where you use up the oxygen and when the oxygen's gone, you're finished. We've got plenty of oxygen and we're going to consume every bit of that. We want to know how much oxygen is required to make that conversion, right? Yes, question?
You left off to phosphorus on the other side.
Yeah, thanks. Okay, so in order to go from here to here, to find out how much that you need, this has to be converted to moles. Okay. So you need, what's the molar mass of P4? You say phosphorus is 30.97. And you need 4 of them. 36, 38, 3, 123.88. Okay. So 6.25 divided by 123.88 is 5.05 times 10 to the minus 2 moles of P4. Okay, so that's how many moles of P4 you got. Now that you got moles, you can go anywhere in the equation. So we're going to go from here to here. So if 1 mole of P4 burns, how many moles of oxygen are required? 5. For every one of these,
Yeah, for every one of those, 5.
you need 5 of those. That's our conversion factor, 1 to 5. P4, for every one of those,
There's 5 oxygen.
5 oxygen. So that's 2.52 times 10 to the minus 1 moles of oxygen are consumed. Okay. Now you can go backwards. Did it ask us mass of oxygen, right? So we got to go backwards. Moles on the bottom, grams on the top, and convert oxygen. So this is 32. That's because there are 2 oxygens and each one is 16. Right? So that one times 32 gives us 8.07 grams of oxygen. Okay? That's why I spent so much time on conversion factors. So much of chemistry is conversions. Okay. Any questions?
Where did the 32 come from again?
2 times 16.
Oh, okay.
Yeah. This is why you need to know what your diatomics are. If a word problem is given to you and says, 6.25 grams of P4, you would have to be given that because you don't know. Are reacted with oxygen. You have to know that oxygen is O2. If you don't know that oxygen is O2, you'll never balance the equation. And the product being P2O5, that would have to be given to you also. So sometimes you can figure out, if you're given reactants, you can figure out what the products are, but most of the time you have to be told because there's so many different reactions that are possible. Okay, let's see. We don't have time for this one, sorry. You need a balanced equation. Methane reacts with oxygen, so you have to know O2, and produces carbon dioxide and water. So you got to be able to write the compounds. Ammonia, that's wrong. That should be NH3.
Yeah, up top they had it right, but they didn't have it right at the bottom.
Yep. Let's see. Here we go. Gotta correct that. What was the question? What mass of ammonia would produce the same amount of water as 1 gram? You got to work one problem and then segue it into the second problem. And we don't have time for that, sorry. It's given to you there, you know, in your PowerPoint. So if you follow the PowerPoint along, you find that if you start off with this many grams of methane, that's so many moles of methane, and convert that to how much water. That will make this much water. Conversion factors again. To replace my batteries. So if this is the amount of water you need, then you just take that amount of water and put it down here. Right here. That amount of water is here, but we're going to make the same amount of water down here and find out how much ammonia is required. Right? So then you take that water and convert it back into ammonia. So there's your ammonia. Oops, sorry. Backwards. Here we go. And we take the ammonia and convert it back into grams. So it's really not as difficult as you might think at first glance. Just break the problem down into small pieces. Okay, concept of limiting reactants. Up to this point, we've had plenty of everything, right? That problem we did before, oxygen is not restricted in how much you have. P4 plus oxygen yields P2O5. But that's rarely the case. Unless you're burning something in the atmosphere, then you got plenty of oxygen. But if you're reacting something in a vessel, you're going to have so much of one reactant, maybe so much of another reactant. One of them's going to run out first. Because it's impossible to get exact stoichiometric amounts of each to where they only react and they're both consumed at the same time. That's theoretical. Experimental error, measurement error alone says that one of them is going to be limiting. One of them runs out first. So that's the limiting reactant, the one that runs out first. It limits the reaction. And this is the artist's idea of, this is a stoichiometric ratio. So you have this many hydrogens, 3 hydrogens, 1 nitrogen. That's perfect. You know, that never happens. This is how it usually happens. In this case, you've got more nitrogen than you do hydrogen that you need. So you're going to use up all the hydrogen, which is the limiting reactant. And nitrogen then is the excess. And it's the same here as it is over here. Right? Here, 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 here. These are the products from those reactions. Okay. All right. Let's just do, I'd rather do a problem. I don't like A's and B's, so I'm going to skip that. I'd rather have real. Yeah. Here we go. No, that carries it even farther. I wanted to do a limiting reactant product before we got to the concept of percent yield. Let's see, maybe, let's use this equation. And fluorine, solid, 4PF3, gas. Okay, so there's our balanced equation. And what mass of P4 is needed to produce 85 grams of PF3? So we know we want this much. And we're looking for what mass here to produce that much. Only the fly in the ointment is we've got a percent yield. All right, so percent yield just means is the actual yield of product divided by the theoretical yield or amount. That's too many yields. Actual amount. And that's in mass. The theoretical amount times 100. That's reality. When you conduct a reaction, you're never going to get 100% of what you expect. It's always less than 100%. In this case, 64.9%. Yield of PF3. So let's assume for the moment that with 100% yield, what would you have to have here? Well, convert that to moles, right? Then make your conversion back to this one and find out how much of that, right? So if we have 85 grams of PF3, we want to convert that to moles. So phosphorus is 30.97, and then 3 times fluorine, which is 19.003. So we want to know molar mass there. I get 8797. 8797. Okay. Divide that into 85. I get 0.966 moles of PF3. Okay. So if we know, and we're still, we're setting this aside for the moment. Assume 100%. We'll deal with that in a second. So this is how many moles of PF3 we have. How many moles of P4 are required to produce that many moles of PF3? Right. So for every 4 of these, you need 1 of those. So divide 4 into this, and you get 0.242 moles of P4, because that cancels that. So that's how many moles we have over here, and we want to find grams. So 30.97 times 4 is the molar mass of P4. All right, yeah, that's right. 123.88. This is grams per mole. So moles cancel, and that times that should be in the neighborhood of 29.9 grams of 4. So with 100% efficiency, or 100% yield, 29.9 grams of P4 would give us 85 grams of PF3. But we only have 0.649% efficiency. So what we're saying is, in order to get this much, we actually have to do the stoichiometry for enough to give us that percent yield, right? So if we take that formula and we say 64.9% equals actual amount, which is 85, divided by theoretical amount times 100, then we can find out what's the theoretical amount we need to shoot for. And that means we need to react that much here to give us this much actual. So solve the equation, right? 100 over here, divide that into it is 0.649, right? Equals 85.0 divided by theoretical. And then the theoretical would be this divided by that, right? Put this over here, right? Algebra, put that over there. So 85 divided by 0.649 is 130.97. So T equals 130.97 grams. So that's what we're shooting for, theoretical, so that we can get actual here. So the calculation we need is 130.97 here divided by 87.97. So that's 1.489. 1.489. And then divided by 4 is 0.3722 times 123.88. It's actually 4.61 grams of P4. So it takes, no, 46.1. 46.1 grams of P4 is required to give us that much yield because of this inefficiency. Okay, so we just worked backwards. We said, all right, if it's inefficient, then how much of this do I actually need to shoot for, theoretically, to give me that actual? That's what this is all about right here. Yeah, 46.1. That's the end of chapter 3. What you can do is start working on your homework and looking at that review document. I think it's divided into 2 sections. The first section is chapter 3, and then you dig down about halfway and you get to chapter 4 review. They're separated in the review. And get started on that, and by tomorrow evening, I'll have chapter 4 lecture posted.
Up on Blackboard or wherever.
Yep, up on Blackboard.
Is it underneath like the Zoom stuff, or
No,
it'll just be on actual regular Blackboard stuff?
yeah, look in Blackboard, start here,
Okay.
then go to, I think it's under Exam2, and then Exam2 has PowerPoints, review documents, and there should be a link in there There's already a link in there for the review that I did last semester.
Okay.
But I started using Zoom too late and I didn't get the lectures in. So I think after this set, chapter 3 and 4, lectures from past will already be there.
Okay.
But I'll still post ours. So you can, it might trigger your thoughts better than something that happened a year ago. Okay, that's it for today. And we'll do the lab next week. So I'll also do a notebook check then. So have the basic stuff in your notebook set up. Okay, let's shut this down.